everyone. My name is Zhenziyu from Georgia Tech, and today I would like to give a short talk about the incorporating intrinsic flexibility effect into morph adsorption properties simulation at a low computational cost. To begin with, I would like to give a quick introduction towards the background for this project. An organic framework, which is morphs, have been widely used in gas adsorption. And separation and capture of gas utilizing morphs are challenging but promising. So what is flexibility for morph? Compared to zeolite, morphs are flexible and have strong influence on adsorption properties. There are mainly two types of flexibility. The first type is intrinsic flexibility, which includes atomic vibration and linker motions without volume change, and it occurs in all materials. The second type is intrinsic flexibility, which is triggered by adsorbate, temperature, pressure, etc. And the figure on the bottom is the illustration of extrinsic flexibility triggered by adsorbate. Some well-known morph properties, say breathing and swallowing, are one of the type. So, as many research have reported, the extrinsic flexibility have a huge influence on morph adsorption. However, these days, intrinsic flexibility has also been shown to be important for morph adsorption properties, especially when kinetic diameters of adsorbing molecules are comparable with small pore size. And in this study, we will mainly focus on the intrinsic flexibility modeling. And I will just start by listing two examples of intrinsic flexibility importance. So Mayank and his co-workers examined the adsorption of 9 molecules in 100 morphs at dilute conditions, which shows adsorption at dilute loadings and selectivity can be significantly affected by flexibility. So as we can see for the figure on the top, the x-axis is the ratio of Horner constant from flexibility prediction and Horner constant from rigid prediction. And we can see a large portion of morphs experience a large change after applying intrinsic flexibility. And the second example is Park and his co-workers found the intrinsic flexibility of morph have a non-trivial impact on serum selectivity adsorption modeling. As you can see from the figure on the bottom, the x-axis is the selectivity from rigid structure, and the y-axis is selectivity after taking intrinsic flexibility into consideration. And we can see these two volumes are not consistent with each other. So after introducing the importance of intrinsic flexibility, I would like to show the current model for intrinsic flexibility. First of all, the quantum mechanism level simulation are not affordable for those systems, mainly because this system is too large. So currently, molecular dynamics are used for this modeling. However, there's two major drawbacks for this modeling. The first one is reliable force fields are not always available. The second is it takes lots of effort to build the model. So we are trying to think up a way that do not require force field and is probably easier to implement as well. So we are trying to come up with a solution by using the experimental information. So what is available in experimental in terms of intrinsic flexibility? So there is a parameter named atomic displacement parameters, also known as atomic vibration parameters and thermal parameters, which is used to represent the displacement ellipsoids. So as we can see from the figure on the right, this ellipsoid for each atom represents the vibration for an atom around its equilibrium state. And this parameter is available in every standard C file and is obtained from XRD. So based on that piece of information from experiment, we are trying to build the model. So this slide is the model details. So overall, this model is based on the snapshot method. And the snapshot method is used to statistically assess a flexible impact. So the snapshot method is a computational approximation to bring down the computational cost by separating framework movement and adsorption process, which is validated and used by previous research. The key of snapshot method is generating snapshots. And in our new model, we just generating snapshots from experimental crystal structure by assuming Gaussian distribution of atom positions and by fixing hydrogen atom distance to heavy atoms to be constant at experimental volume and we correct neighbor atoms by average displacement. And we also rescale temperature from experimental data using Boltzmann distribution. So this workflow on the bottom is an illustration of our ellipsoid method. So the only input for this whole model is the experimental save file, and by going through in-house Python code, we'll generate a bunch of flexible snapshots. And each of these snapshots will go through GCMC, and the overall results from the GCMC will be averaged, and this would be regarded as the adsorption property prediction with flexible influence. So to give a quick summary of the background and the model details, I'll just make an example here. So for example, this structure, as we can see, the left figure is the rigid structure, and traditionally rigid structure is used to give adsorption properties. And now we argue that, based on the previous research, the intrinsic flexibility have non-trivial influence on adsorption properties. Say when you take into consideration of the atom vibration and link rotation, those type of intrinsic flexibility would change the pore size distribution, as we can see from the figure on the right. After taking consideration of flexibility, the pore size distribution is just more wide, and thus have an influence on the adsorption property. And currently, to model this type of flexibility, the molecular dynamics is used to describe the Moore framework movement, which is not an easy task. So we come up with a method which is based on the experimental information, and this method will enable us to model the Moore intrinsic flexibility at a much lower computational cost. So in terms of the simulation result measurement, qualitatively, the intrinsic flexibility is important if the p-volume of one sample one tail t-test is less than 0.1 or greater than 0.9 for result from flexible snapshots and rigid structure. This is, in other words, is a statistical test of whether the rigid structure is statistically different than the flexible snapshots method result prediction. And quantitatively, if flexibility importance is 0.75 or greater than 1.25, we consider the intrinsic flexibility to be important. The flexibility importance is merely a ratio of flexible structure adsorption mean volume divided by the rigid structure adsorption volume. So this is two result measurements. So after we develop the model, we'll definitely first validate it. So from this slide, I will just introduce the model validation results. So we picked around 20 random morphs from CoMorph database to predict adsorption and dilute and non-dilute condition of 7 isobates. We then used the traditional MD method and our newly developed ellipsoid method to give flexible Moore framework adsorption property predictions. In terms of the simulation results, first, according to MD results, intrinsic flexibility is important in 55 cases in non-dilute systems and 29 cases in dilute systems. So, again, consistent with the previous research, we show that intrinsic flexibility is important in Moore adsorption property prediction. And the prediction from the ellipsoid method are compared with the prediction from MD method. And these two sets of prediction are qualitative consistent in around 90% in both dilute system and non-dilute systems, and quantitatively consistent in around 40% in non-dilute and dilute systems. And in the next slides, I will try to introduce make some two examples of how this data illustrate. And I just pick 5 morphs out of 20 morphs as the illustration here. For the left figure is the prediction from ellipsoid prediction, which is blue dots, and the orange prediction, which is MD. And we can see from here, the y-axis is the flexibility importance. And these two methods usually have the quantitatively consistent prediction, which means they can predict whether the intrinsic flexibility have a positive influence or have a negative influence on the adsorption properties. However, in terms of the quantitative prediction, these two methods usually have a little bit differences. So that's the reason why the consistency is a little bit low in the last slides. And for the right figure is the prediction for a Henry constant, and we can get the same result, same conclusion. So overall, the conclusion would be our ellipsoid method qualitatively predicts the importance of more flexibility on adsorption. And in this slide, we'll try to apply our model into a new set of the morph, which is anion polymorphs. We picked 4 anion polymorphs to simulate the adsorption isotherms using both rigid structure and 2 flexible structure. And all the results are compared with experimental results. And here in this slide, let's just pick 2 examples of the simulated results. And we can see for the figure on the left, which is figure A, it is the methane adsorption. And we can see from the figure, all the rigid flexible isotherms are all very close to the experiment data, which is this black dot, which means that the intrinsic flexibility is not important in this case. However, in the right figure, we can see all the rigid prediction is a little bit far away from these black dots, while our flexible prediction, which is the red line and purple line, are much more closer than the experimental prediction. However, admittedly, they're still not close enough towards the experimental observation. So the main takeaway from this slide is, first, often rigid results do not agree with experimental isotherm. Second, our ellipsoid method qualitatively predicts the importance of more flexibility on isotherms, but more accurate method is needed to fully capture the experimental isotherm. Besides morph, we also apply this method on amorphous materials. So ellipsoid method can give a qualitative prediction of the importance of more flexibility without using a force field. The main takeaway is like it can predict the importance of flexibility without using force field. And for amorphous material, the access to reliable or transferable force field is usually challenging. Notably, there's some simulation details we need to point out. Because none of this structure comes directly from experimental data, which means like the atomic displacement parameters we previously used are not directly available. So we tackle this problem by using average displacement parameters from a collection of crystal materials. For example, in amorphous materials in database, the atomic displacement parameters from crystal ZIF experiment data will be used. And if the corresponding crystal materials are not available, the mean displacement from COMOF database will be used. So here I just used HCP as example. As you can see here, for the left figure is the methane adsorption isotherms. And I can see each point, the p volume in the isotherms are all below the threshold. This means like the rigid structure has no difference with flexible snapshot statistically. And also the flexible importance is between 0.9 to 0.1. So overall, the increased flexibility is not important for the methane adsorption in this material. However, for the hydrogen adsorption is another case, which the increased flexibility does show its importance. So, to give a summary, a method that can give qualitative prediction of the importance of more flexibility on adsorption without using force field for morph is developed and validated using 20 morphs from COMOF database. And we have applied the new method on anion polymorphs and amorphous material. And this new method can be used, first, for newly synthesized material, rapidly assess if intrinsic flexibility matters for potential adsorption replication. And second, it can be used before building complex model and enable you to have a general idea of whether it is worthwhile to build a complex model. And finally, this method can be used for material where access to reliable or transferable force field is challenging. And finally, I would like to acknowledge the funding source, the Department of Engineering and Energy, and also I would like to thanks our group member for supporting this. And I would like to take any comments or questions in the live chat section or the Blue Jeans meeting room. Thanks so much.